They have to balance binary search tree, binary search. The search word is important because that means if we have some value, the left node would be less and the right subtree would be more. This is a search. Now, how can we make sure that it is balanced? There is a known technique like rotations and some other algorithms, but the simplest one is built from scratch. And the building pattern is that we build left, then make current, and then we build right. And to make sure that it is balanced, the count of children on the left should be equal to the count of children on the right. So this is like balancing, and the middle should be middle of an assorted array. That makes the tree balanced. So if we have some subtree, this count left equal to the right count. That means it is balanced. It can be differ but by some small value, but it should be almost equal. It's not official, but this is how it works in practice. So we have sorted array, and in the middle we have current tree node, and this would be left and this would be right subtree. And for the subtrees, this pattern will repeat. So this would be mid, and this would be left and right. And the same for this situation. Now we know how to build the balanced subtree, but how can we make this sorted array? We can do in of n log n, just read all values in a tree and then sort them. But we have conditions that by definition our tree is already search tree. That means if we do like a special traversal, so we have pre-order traversal, in order, and post order. Pre-order is you have to do current, left, right. In order it is left, current, right, and post order is left, right, current. So we interested in this in order traversal, and it will give us the correct sorted visiting of the current nodes. So if we visit the left, current, right, this is in order. So after left we visit current, and after current we visit right. And when we visit, we can put the current into some, put in a list, and this would be a sorted list. So it would visit, it would go down to the smallest value and put it here, like smallest. And then the middle value would be like middle, and the last one would be largest. This is how it works under the hood. Let's look at the code. This is very simple code. Just use global variables for the list, then write this depth first search recursion of in order traversal. So left first, then current, put into list, and then the right. Now don't forget to invoke this function, and the build function is the same as we described earlier. We have middle of from and to coordinates, and the middle is the value. Now after we build the current, we visit left side, it is from, and make sure you don't have off by one errors, just exclude everything. So make the range inclusive. That would make it simpler to exclude values. So we exclude I is the middle, and with right. And this condition tells us that we out of any values, just from bigger than 2. So this is a simple algorithm. Now let's look at what can we do with this algorithm. It's too early for the Rust. Let's look at the Kotlin. So this is how we can compress this Kotlin. Just use the build list. Then so this is basically the same, but we don't define what we put into list. We put the 3 nodes itself into the list, and when we build them, we just take this value from the list and mutate the left and right coordinates. So it's kind of memory efficient, but still the memory is the time complexity is of n, and the space complexity is O of n, because we have to put entire list, entire tree into list. Now let's look at some fun solution like this one, or not, it's this one. So we can use lazy iterator. So the lazy iterator is that we start building before we collecting anything. So we just make this Kotlin lazy iterator, and we, instead of this left and the right coordinates, we put the length of this entire subtree. So we have to count how many values we have before doing anything. Now this we go build left subtree. Obviously we do this kind of and divide it by 2. The subtree is half, left subtree is half. Now then we take the next from the iterator, and now let's look at the iterator itself. it is just a DFS of the original tree. So it is a DFS of R, the root, and it goes like this. It goes left, then it yielding the current node, and after that it goes right. And right, we saving this pointer because inside building we already modified this pointer after the next. So after yielding the next, the right pointer would be modified. So we have to preserve it to correctly iterate to the right subtree. So this is how it works, and the memory complexity of it is actually better. O of logarithm n is memory complexity, because we are not saving any list of all the numbers, only the depth of this recursion. So before yielding, it have internal stack and state machine. Now let's look at the Rust solution where we don't have this lazy sequence. And I asked Gemini to implement it for me, and it did it with stack. This stack is vector, and the pointer is this one, the C current pointer. Now, what it does the same. The C is count, so we count how many nodes we have. Now, after that, we go to the left subtree, build it, and then we iterating, taking the next from the iterator, and it gives us options, so we map it, and then we modify. The left is pointed to the left subtree, and the right is to build the right subtree, and then return the current node. Now, how this stack iteration works? It is just the same depth first search in order traversal. So it takes the current node, and it saves it into current, and it pushes to the stack. Now, after that, it pops the stack. So it goes on the left as much as possible, while it have some left. Then the pops values. And after it popped value, it modifies the current value C pointer to the right node and returns the current. So this from fn iterator always will return the current node, and the current is always like go to the left as much as possible, then pop, and now we have the current. So this is how it works, and that's it for today.